Cool guys. This is the following day. I started breaking this down yesterday. It's a very simple and should be a very straightforward problem. This is the peak finder. Um, find a peak element. Easy problem, actually a median. Yeah, let's break that down. Peak element is an element that is strictly greater than its neighbors. Given a zero-indexed array nums, now find a peak element and return its index. If the array contains multiple peaks, return the index of any of the peaks. It has multiple peaks, just returns one. You may imagine that, yeah. So I designed the constraints here yesterday, and we are good to code. I think I have two approaches here. Draw the line. It's like 1, 2, 3, and 1. Picturing a graphic composition of the array, showing what a peak is in a very handy way here to understand. And then I started to work on the brute force solution first, which basically have a few conditions here and cases. When the item and the peak is the first item, when the peak is the last item, considering the nature of the infinite, of the outside scoped items, and also the ordinary use case here. So if I is 0 is the first item and is greater than x, return it, and if I is n minus 1, which is the number of the array and the last index, it return also the occurrence because it will be there, and otherwise we're going to iterate and iterate through the array, the whole array, and return CR. That's ON. That's not what we want. Tackle this problem, which tackles it in a logarithmic time, which is O log of n, which reduces the time on the opposite hand of exponentially. That means it divides the computational time by 2 for each iteration. So instead of O of n is O log of n, basically. How that happens, so it sounds pretty cool, but when we're talking, but it's not that cool if we are working on it. Let me get one of the arrays here that we have on the use cases. Let's start working on it. We have this array here, for example. So what we do, we use the array tools that we have. Basically we have n, and then we have n minus 1, we have 0, and we have the middle of the array, which is this is right, and this is middle of the array, right? So with that being said, we need to start basically breaking down. We have control of the array here. One of the things that we learn here is that we can control the array, and then if we have those things here, we have it on our hands. Basically we can break it down, divide into, and that's what we're gonna do here. So that's the middle of the array, but I'm actually wrong here. It's left. In this case we will have a kind of dynamic middle, so we don't want to use n divided by 2. We have another type of interaction that we want to provide to this machine process, basically. What we need here is really simple. Where am I going with this? Understanding that we have peaks here, so it always goes to a direction. So let's say that the peak is 3 here, it goes to the right direction, and then if we start if the middle is here, it goes to right, and if we find the middle is in the 1, it can go to the left and it can go to the right. So we can go both directions. and that's something that we would like to understand, because we always go to one direction. We just want to go to the left or to the right. We don't want to and then we want to break the array based on that basically definition that will tackle the problem. So the problem is we need to find the peak. So the peak will always be the highest value, right? So the thing here is we have an array, we need to find a peak, and that should be the thing here. And then we'll have basically these items here. If middle is here, we'll have middle, we'll have right, this is right, and this is left, right? It's a bit small, but you can see the pointers where they are positioned, and that's the middle, right? Very cool. I'm sorry for you if you're watching this on a cell phone, but I recommend you to study on your computer if you're studying algorithms, but I hope that helps you. So yeah, just a bit of a distraction here. So we are now on the middle, we have left and right, and that's the thing that we want to do here. We want to go to somewhere. Where we want to go, where are we at? Now we know where we at, and we're gonna go to the greatest item, greatest neighbor, to the highest neighbor. So if I will start a comparison first. So and I say if nums middle is greater than right. One thing is here that I need to return the array index, not the num itself, right? Not the value. So if nums middle is greater than right, what we're going to do, if this is greater than right, if nums in the middle is greater than right, that means 3. In that scenario, will be something like this. Let's say that here is 6. Here is 6. Here is 6 actually. And you can see that here is 7 and here is 8, for example. If that, so if we have this specific scenario here down below, we have middle, which is greater than right. What should happen is we're going to put right to the middle, and middle is going to be here, right? And then we'll have left and right. And then we're gonna do it again. If we have a look here, we will see that the goal of the algorithm is to basically find the peak. We already have the peak at this point here, but we didn't finish our iteration basically. So that means we have the peak, we know that is greater than left and right, but what we would like to do to finish the iteration here is like keep moving and reducing the left and right till they crash into the actual peak basically. So we still have a few interactions to do that. How do we do actually this? After we have set up all pointers here, our pointers here, we do need something else here. So what we're going to actually do here is like we have these items, and we have left, and this is left, and this is right, as we know. And I'm gonna ask myself here, is middle greater than right? So if middle nums middle greater than nums height, what we do, we move the pointer greater than the right. That means that this part of the array will be, you know, higher in this case, which is not this case, right? But that can happen. So when we have the other hand side here, right, I'll make it less, you know, annoying here. But we have these two, you know, divisors here that will hold the peak. The peak will be in one of these directions, basically. So if middle is greater than right, that means the peak will be on the left. And what we need to do, we need to move this item here, which will be the foremost right, and the foremost left. So what we're gonna do here, I'm gonna move this guy here to the middle, right? And then the middle will be exactly left plus right divided by 2, right? That will be here. If it was on the opposite hand side, what's going to happen? If it was on the opposite hand side, what we're going to do is, like, it will be here, right, will be here. And what is happening is, in this specific use case, is that as we have middle here, we don't need to move left to the middle. We could move left to the left hand side, right hand side of middle, because it was already counted there. So it's like we counted it before. It wasn't our, you know, it was our actual middle, so we actually can skip it and it will be middle plus 1. So, and that means that the middle here will be here, for example, right? And logic here again, we're going to ask, is nums mid greater than right? Yes, it is. So what's going to happen? I'm going to move my right pointer, right? And I'm going to calculate a mid, which is going to be here. So 0, 1, 2, 3, 4, 5. 5 plus 4 divided by 2. That means 9 divided by 2 is 4.5. So it'd be 4, 1, 0, 1, 2, 3, 4. So that will be my middle now, right? And I'll ask again, is my middle greater than right? No, it is not. So I'll put my left hand pointer here in the middle, and then we will return left, basically. We need to, it's very interesting because at some point we have the peak before the iteration actually finishes, but that's how we usually sort it to the end, basically. Then that we're starting back to iterate back again, and we have, if nums mid is greater than nums right, that means I will have the left portion available to iterate. And what I want to do is say that right is equal middle. So if I say right is equal middle in this case, it will work. Okay, and else that will mean that left is equal middle plus 1. Why? Because in that case, if my mid number is not greater than right, that means the right is greater than my mid. And then what I'm gonna do, I'm gonna iterate back here again. So that's what we did, basically. And then I can just return left, as we previously seen there, because we need to finish the loop as we had there in that occasion. So that will do. I'm almost sure that that will do. Now, after putting things in the board and understanding the algorithm, we can actually start coding. So what the first thing that we would like to do is set the pointers here. I'll say that let n is equal nums.length just to make it more practical here. And then we're going to have let left is L is equal 0, and let R is equal n minus 1. So we have the basics there, and then we can say that let mid is equal left plus right divided by 2. That's right, and I'll set a math on the floor here on these. So we'll have a mid there. So in while left greater than right, we could start iterating. We will iterate respecting this here, what we said. So yeah, I could even put this inside a loop. Will make a difference. I don't think so. Let's see. So if nums mid greater than nums right, so right is mid plus 1, and left is equal mid minus 1, right? What we're going to do, I don't even know if I'm using this, but yeah, it's greater than right. What we would like to do here is nums mid is greater than right. We will have the left portion, and that means I will say the right is equal mid, and else I'll say that left is equal mid plus 1, and then I'll return left. Right? I hope that works in the code. Let's see here. Submit it. That is something I did wrong, obviously. Nums mid is greater than nums right, and mid is math floor L plus R divided by 2. So in right is mid plus 1. R is equal M. And R, I'm screwed, yeah. R goes to the middle, left goes to the right. And then return L. So what's the point here we are not covering? Oh, main signal here should be fine. Yeah, that's it. Not perfect, but submitted. Back again. Okay, seems to be fine. Okay, cool. That's it, guys. Thanks for watching. Keep tuned for more algorithms.